Have you ever wondered how it all ends? I mean, really ends? Not just for us, but for everything. Every star, every single galaxy, the very fabric of space and time. Well, today, we're going to dive into one of the most violent, most spectacular possibilities out there, the Big Rip.
Okay, so to really wrap our heads around what the Big Rip actually is, we're going to do something a little different. We're going to start at the end and work our way backward. Let's imagine a countdown to the universe's final moments. And this is based on a model where the cosmos doesn't just, fade away quietly. No, it gets violently shredded.
What's just wild here is the scale, right? And the speed of this total destruction. It starts out huge and then gets terrifyingly small and personal. So, with 200 million years left on the clock, the biggest things we know, galaxy clusters, they get pulled apart. Then, skip ahead to 60 million years out, and gravity can't even hold a single galaxy together. Our own Milky Way just starts to dissolve. But it's the final stages that are just mind-blowingly fast. 3 months before the end, the solar system is toast, gravitationally unbound. Then, just 30 minutes out, the Earth itself is torn apart. And in the very last, tiniest fraction of a second, the fundamental forces fail. Atoms themselves are ripped open. Everything just gone, erased.
I know. This sounds like something straight out of a sci-fi movie, right? But here's the thing. The Big Rip isn't just some wild fantasy. It's a genuine, potential outcome that comes directly from our best understanding of the cosmos. So, let's dig in and unpack the actual science that makes this terrifying scenario even a remote possibility.
So where did an idea this extreme even come from? Well, the story of the Big Rip doesn't actually start with the end. It starts with a shocking discovery about how our universe is expanding. A discovery that completely flipped modern cosmology on its head.
You see, for most of the 20th century, ever since Edwin Hubble figured out the universe was expanding, the big question was pretty simple. What happens next? And the prevailing thought, the thing everyone pretty much agreed on, was that gravity would eventually win. All the stuff in the universe would act like a giant brake, slowing the expansion down over time. People thought it would either coast to a halt or maybe even collapse back in on itself.
But then, 1998 happened, and everything changed. Two totally separate teams of scientists were looking at these really distant supernovas, and they noticed something weird. They were dimmer than they should have been, which meant they were farther away than all the models predicted. There was really only one mind-bending explanation for this. The expansion of the universe wasn't slowing down. It was speeding up. This was such a monumental discovery, it won a Nobel Prize.
So, to explain this completely bizarre acceleration, scientists had to come up with something new. They gave it a name that sounds mysterious because, well, it is dark energy. This stuff, it's not matter, it's not light, it seems to be a property of space itself, like a kind of cosmic anti-gravity that's pushing everything apart. And here's the real kicker. This isn't some tiny fringe effect. Dark energy makes up about 68% of everything in our universe. The vast majority of the cosmos is this mysterious stuff.
But here's the twist. Just having dark energy isn't enough to get you a Big Rip. That doesn't automatically happen. No. For that to be on the table, you need a very specific and, frankly, very strange kind of dark energy. You need a phantom ingredient.
And this is where things get really weird. Think about it. Normally, when space expands, anything inside it gets diluted, right? It spreads out. But phantom energy would do the exact opposite. As space expands, the density of this phantom energy would actually increase. This creates an even stronger push, which causes space to expand even faster, which in turn creates even more phantom energy. It's this terrifying runaway feedback loop that just spirals out of control. So how can we possibly tell what kind of dark energy we're dealing with? Well, cosmologists have boiled it all down to one single critical number. It's represented by the letter W. You can think of W as a measure of how pushy dark energy is. And the precise value of this one little number, that's the key. That's what will tell us our universe's ultimate fate. And this really lays out the two main paths, the two possible futures. On one hand, if W is exactly -1, then we have what's called a cosmological constant. Its density stays the same, leading to a steady acceleration and eventually a cold, empty big freeze. But if W is even a tiny bit less than -1, say -1.1, then you're in the phantom energy zone. And that's the path that leads straight to a Big Rip. Now, the Big Rip is definitely the most dramatic ending imaginable. But it's not the only horse in this cosmic race. So let's take a quick second to put it into context with the other big ideas about how the universe might end. So here you have it, the three main contenders for the ultimate fate of the universe. You've got the big freeze, which is driven by that constant dark energy we just talked about. Then there's our main event today, the big rip, caused by that runaway phantom energy. And finally, there's the big crunch. That's an older idea where gravity eventually takes back control, reverses the expansion, and everything collapses back down.
Okay, so what do most scientists actually think is going to happen? Where's the consensus right now? Well, this quote really sums it up pretty perfectly. The Big Rip is not the favorite theory. Based on all the data we have right now, the Big Freeze seems like the most likely outcome. The evidence just doesn't seem to be pointing toward that crazy runaway phantom energy.
But hold on, most likely doesn't mean guaranteed, right? In science, it all comes down to the data, to the actual measurements. So let's get to the bottom line. What is our best, most precise measurement for that all-important W parameter?
And here it is. This is the number. Our most precise measurement for W, thanks to the Planck Space Observatory, is -1.028 plus or minus 0.031.
So what does that number actually mean? Well, that central value, -1.028, is incredibly close to -1. That points very strongly towards the big freeze. But, and this is the crucial part, you see that little margin of error, that plus or minus 0.031? That's everything. Because of that uncertainty, the true value could still be, say, -1.05. It could still dip just below -1, and that means the big rip is still on the table. It's lurking right there, at the very edge of what we can measure.
And you know what? Pinning down that number, eliminating that uncertainty, is one of the biggest goals in cosmology today. That's exactly what the next generation of amazing observatories is being built to do. Missions like Euclid and the Nancy Grace Roman Space Telescope are going to map the universe with unbelievable precision. By figuring out exactly how galaxies have spread out over billions of years, they hope to finally nail down the true value of omega and give us a much, much clearer picture of our ultimate destiny.
So, for now, the question just hangs there, doesn't it? Will our universe end in a silent, endless freeze or a final, violent rip? The evidence seems to lean one way, but the possibility of the other still remains. The answer is out there, hidden in the darkness between the galaxies, just waiting for us to find it.